there, and welcome to This Explainer. I am so incredibly excited you're joining us today. We're going to be diving into one of the most fundamental and honestly completely fascinating rules that governs our universe on a microscopic scale. We are talking about covalent bonding. Think of them as the invisible handshakes that literally hold our world together. So if you've ever found yourself wondering exactly how atoms manage to build the water we drink, the air we breathe, or even the plastics we use every day, well, you are definitely in the right place. All right, let's take a quick look at our agenda for today. First up, we'll explore the art of sharing. From there, we'll walk step by step through single bonds, double bonds, and triple bonds. And finally, we'll wrap things up by comparing their properties in a covalent showdown. Let's get to it. Section 1. The art of sharing. Why exactly do atoms co-own electrons? Now, in chemistry, it really is all about stability. But why do atoms interact with each other to find it? Well, imagine this. You desperately want a bicycle to commute to school, but you only have half the cash. Your friend also really needs a bike, and they only have half the cash too. Neither of you can pull this off alone. So what's the solution? You pool your resources. You buy the bike together and co-own it. By sharing, you both get a stable, reliable ride. And you know what? Atoms behave in exactly the same way. When nonmetal atoms need electrons to fill their outer shells, and they can't just take them from someone else, they pool their resources. They share their outermost electrons to achieve a perfectly stable, full valence shell, just like the noble gases. Let's formally define what this sharing actually looks like in chemistry. A covalent bond is the strong electrostatic attraction between shared pairs of electrons and the positively charged nuclei of the sharing atoms. Because these electrons are shared so incredibly closely that the atom's outer shells physically overlap, this bond is super hard to break. It's a mutual attraction keeping the whole shebang tightly locked together. Moving on to Section 2, single bonds, the classic one-handshake scenario. This brings us to the single bond family, which is basically the simplest form of sharing. We're talking about molecules that rely on sharing just one single pair of electrons between any two atoms so they can hit that stable, noble gas configuration. We'll start with simple elemental molecules like hydrogen and chlorine, and then we're going to graduate to compounds like hydrogen chloride, water, ammonia, and methane. If we were to map out a dot and cross diagram of a single bond forming, it basically happens in 3 steps. First, the non-metal atoms approach each other. Second, their outer electron shells overlap. And third, one pair of electrons, so one dot from one atom and one cross from the other, is shared right there in that overlapping space. Take chlorine, for example. 2 chlorine atoms each have 7 outer electrons, right? They just need one more to reach an octet. By overlapping and sharing one pair, boom, they both get to eat. It's the perfect compromise. We see the exact same thing in hydrogen chloride, where hydrogen gets its duplet and chlorine gets its octet just by sharing one pair. Let's strip it back to the simplest molecule in the universe, hydrogen gas, or H2. Each hydrogen atom only has 1 electron, but it really wants 2 to be stable, just like the noble gas helium. So 2 hydrogen atoms overlap their shells, bringing their single electrons together into a shared pair, 1 dot, 1 cross. That is one single covalent bond, perfectly completing the shells for both of them. But here's the thing. Atoms aren't limited to just one partner. Take water, for instance, H2O. An oxygen atom has 6 valence electrons. It needs 2 more to hit that magic octet roll. Now, since a hydrogen atom only has 1 electron to offer, oxygen actually needs 2 completely separate hydrogen atoms. It shares 1 pair of electrons with the first hydrogen and a second pair with the other. Oxygen gets its 8, each hydrogen gets its 2. It forms 2 completely separate single covalent bonds. We can actually scale this up even further with ammonia, NH3. Nitrogen sits in group 15, so it has 5 electrons in its outer shell. To reach 8, it needs 3 more. So what does it do? It reaches out and forms single bonds with 3 individual hydrogen atoms. That's literally 3 single handshakes happening all at once around a central nitrogen atom. And to bring our single bond journey to a climax, we have methane, CH4. Carbon is basically the ultimate sharer. It has 4 outer electrons, meaning it needs exactly 4 more to become stable. So it forms 4 distinct single bonds with 4 hydrogen atoms. If you look at a dot and cross diagram of this, it is beautifully symmetrical, 4 shared pairs perfectly arranged all around the central carbon atom. All right, Section 3, double bonds, the double grip. What happens when one pair just isn't enough? Right, so what does happen when a single handshake doesn't provide enough electrons to reach stability? Think about the oxygen gas in the air we are breathing right now. Oxygen atoms need 2 electrons to be stable. If 2 oxygen atoms bump into each other, a single shared pair leaves them both sitting at 7 valence electrons. That's not 8. That is definitely not stable. So how do they fix this? They use the double grip. Instead of just shaking one hand, imagine grabbing both of your friend's hands. The oxygen atoms push closer together, and they share 2 pairs of electrons in their overlapping shells. 2 dots, 2 crosses. That's 4 shared electrons in total. We call this a double covalent bond. And as you might guess, it creates a much tighter, much stronger connection than a single bond. It gets really interesting when carbon and oxygen team up to form carbon dioxide, CO2. Carbon needs to share 4 electrons. Oxygen needs to share 2. So the central carbon atom forms a double covalent bond with an oxygen atom on its left and another double covalent bond with an oxygen atom on its right. It creates this beautifully rigid straight line, a completely linear molecule, locked together by 4 shared pairs in total. Which brings us to section 4, triple bonds, the strongest holds, the ultimate bond. So we've done 1 pair, and we've done 2. Can we go even further? Absolutely. I really want to emphasize the number 3 here. Let's look at nitrogen gas, N2, which actually makes up about 78% of our atmosphere. A nitrogen atom has 5 outer electrons. It desperately needs 3 more to fulfill the octet role. When 2 nitrogen atoms meet, they don't hold back. They share 3 pairs of electrons. 3 dots, 3 crosses. 6 electrons living right there in the overlap. This triple bond is incredibly strong, and it's exactly what makes nitrogen gas so unreactive and stable. All right, section 5. Let's compare these covalent bonds in a little showdown. We've seen the single handshake, the double grip, and the triple hold, but how do they actually stack up against each other in physical reality? Well, the absolutely crucial point here is this. The number of shared electrons fundamentally changes the structure of the molecule. In a single bond, like hydrogen, with just 1 shared pair, the electrostatic attraction is relatively mild, so the distance between the 2 positively charged nuclei is longer. But in a triple bond, like nitrogen, with 3 shared pairs, there is a massive concentration of negative charge right in the middle. This powerfully attracts those positive nuclei, pulling them incredibly tightly together. When we map it all out, we see a really clear pattern. As we progress from single to double to triple bonds, the number of shared pairs obviously goes from 1 to 2 to 3. Because of that increasing electrostatic attraction, the bond strength goes from weakest to strongest. And correspondingly, because the atoms are pulled closer together, the bond length goes from longest to shortest. A triple bond is absolutely the shortest and strongest bond of them all. Because of this, there is a fundamental rule when it comes to chemical reactions. Multiple bonds are stronger than single bonds, meaning a lot more energy is required to break them. Remember, bond energy is the amount of energy absorbed to break 1 mole of a chemical bond. To put that into perspective, breaking a single carbon-carbon bond takes about 350 kilojoules per mole, but breaking a double carbon-carbon bond requires 610 kilojoules. That is a tremendous difference in physical reality. So as we wrap up, I want to leave you with this provocative thought. How do these microscopic, completely invisible handshakes, whether they're single, double, or triple, dictate the physical properties of literally everything you touch, eat, and breathe? It's pretty astounding to realize that the entire architecture of our physical world relies on atoms just trying to find a little stability by sharing what they have. Thank you so much for hanging out with me on this explainer. Keep questioning, keep learning, and I will see you in the next one.